I need to record it, thank you. We need to first, we've got to come up with the shortcuts, right? So we're going to start easy, and we're going to work our way into a couple harder, more useful ones. So here's the first one. I need to introduce a little bit of notation to you, too. Okay, derivatives. Okay, so here's some different ways of saying derivatives. We're not going to use all of these, but different books use, different versions of this. So if we have the function y equals f of x, these are all ways of saying the same thing. These are all ways of writing the derivative. But one of them we already know, f prime of x. Okay, that's a good one. That's a really good one because the prime indicates that we have taken the original function and we have tweaked it through differentiation. Okay? Here's another one. dy dx. Okay, what is that? That's another way of saying derivative. So that's also not a bad way. And I'll show you why that's not a bad way. So you'll remember this one now after I show you this little trick here. So if this is the xy plane, and here is my function, f, right? Okay, well we said that the slope of a secant line between these 2 points has the form rise over run, right? Slope of a secant line we might call delta y over delta x, right? Where delta means change in. And that's how we drew our slope triangle. That all looks familiar. Okay, but what about if we want to shrink delta x so it goes to 0, and we want to find the slope of a tangent line at x? Well, then the slope of the tangent line we would write as a really, really small delta y over a really, really small delta x. So what this really says is this is kind of a shortcut way of saying the slope of a tangent line, dy dx. Okay, so that's also a notation that I really like, that makes sense. Okay? The other way that we will probably see it this year is something very similar. We could also see something like this. That's a way of saying the derivative process. So that's the derivative of something. Like we could do, for example, the derivative of x squared. And what that's really saying is equivalent to if f of x equals x squared, then f prime of x equals whatever that answer is. Equals the derivative with respect to x of x squared. Yes, sir.
Are all 1, 2, 3? Are they all equal to each other?
Yeah, they're all identical. There's just different ways of saying. Now, this is a specific. I just threw in a function as an example, but that could be any function, right? I just picked x squared. That could be sine x or tangent x or anything, right? So those are the main ways of writing derivatives. We could also, I guess, kind of combine 1 and 3, and sometimes you'll see this. You could say something like the derivative with respect to x of f, or f of x. That's fine.
So this is all just...
Yeah, these are all, if you see any one of those, they're all interchangeable. Okay? I would say that probably, the main ones are 1 and 2. We'll sometimes fall back on this. And they do kind of have their own little flavor. I mean, if we're talking about slopes of tangent lines, well, dy dx is a pretty good way of doing it. If we're talking about, rates of change, then this is kind of a good way of expressing it, right? If we're taking, like, for example, in physics, if we take a position function and we want to find the velocity function, well, we would say something like this, right? We would say if position is d of t, then the velocity function, see, this is why I really hate d. That's what you see, now you're starting to see why. Because then when we say something like dd, I mean, that's kind of dorky, right? That looks bad. That's why when you take like a college physics class, or a calculus-based physics class, they would never pick D for position, they'd always pick S, right? And then, so let's just say hypothetically here, we're not gonna be doing a lot of calculus in our physics class though, so it'll be okay. But in here, let's go ahead and say that position is given by S of T, okay, instead of D, so it's gonna be S. Then V is equal to ds dt, or maybe even better, S prime of T, right? Because we know that instantaneous velocity is the derivative of position physics types, right?
Yeah.
Because that, it corresponds to the slope of the position function, right?
Right.
Okay.
Number 4, what's in the bracket?
Just an F. An F. So those are just, and they'll, trust me, this is, if it seems like a lot of stuff, it'll be a complete non-issue. As soon as you get working on it, it'll just all make sense. Okay, so what we want to do today though, what we want to do today is we want to come up with some rules. We're going to come up with some derivative rules that we can use to avoid having to use limits to take derivatives. Here's the first one that we want to get. The derivative with respect to x of a constant. So C is just going to stand for some constant. What is, do you think, the derivative of a constant going to equal? We can think about it graphically, because this is the function that we're differentiating, right? What do you think?
0.
It's 0. Yeah. Why is it 0? What's your justification for that, David? What were you thinking?
Because if it's just a constant, it's going to be a flat line.
Yeah. Okay, good. Because if we take the function f of x equals c, or y equals c, what is that? If it's a constant, it's just a horizontal line, isn't it? That crosses the y-axis at c. What's the slope of that line? 0. So there's one justification, so we know what the answer is going to be. It's going to be 0. Let's see if we can show that analytically, though. The way, this is typical in math, if we want to come up with some kind of a shortcut, a formula, if you will, then we've got to start with the fundamental definition of something and show that it's always that way, right? This is what math does. This is, anything that we can say in math that is completely general is very powerful. We would prefer not to say specific stuff. We want to say stuff that's broadly useful, right? So if we want to prove this, then we really do need to go back to our original limit definition and show that this works. So the derivative with respect to x of c in terms of a limit definition, that's just like f prime of c, right? What's that equal to? Well, it's equal to, here, I tell you what, let's even do it this way, just so it looks more familiar. Let me write it out this way. So our function is just f of x equals c, right? So let's start at the beginning. What's our definition, you know, our difference quotient definition of a derivative? F prime of x equals a limit of what, in general?
F of x plus delta x minus f of x
Over
delta
as, good. Okay, so all we have to do then is we just have to plug in the specific. Well, the only specific thing here, we're not going to pin this down to a specific value of x, but we want a specific function. So if f of x equals c, then what's f of a? No.
c
C. Yeah. What's f of z?
c
C. What's f of x plus delta x?
c
C. Do you get that? There's no connection. Now, if we got an answer, like if we had f of x equals some formula that involves x's in it, then every place where we had an input value of x, we'd have to have an output value of x. Every place where we had an input value of a, we'd have to have reflected in our output that a, right? But is there any connection between the input variable x and the output constant c?
No.
No, there are no x's in our answer. So the answer is always c, regardless of what the input is, right? So this gets pretty simple then. We're just taking the limit of c minus c over delta x as delta x approaches 0. So what do we really get for our answer then?
0 over
Well, on the
delta
top we
x,
get,
0 over delta.
okay, we get 0 over delta x is approaching 0. So do we get 0 on the bottom?
0
Kind of. But it's not really 0. It's really a small number, isn't it? Does that make sense? As we approach 0, we're never actually at 0, are we? So the bottom, yeah, it's 0, but it's really what we might call a 0 plus or a 0 minus. We haven't specified from the left or the right, so I'm just going to call it a small number. You get the idea, though?
Yeah.
True 0 divided by any number is what? 0. So there's our answer, 0. Okay, make sense? Okay, so there's one. We got one in the bag. How about that? There's one that we can use from now on.
Every time, how do we know that it's 0?
How do we know what?
Never mind, just keep going.
No, that's a good question. So
when d is over d of x, and then there's a constant and it's always 0.
So what this is saying is the derivative of
Okay.
any constant is equal to 0.
So even if you said, even if it's f of x is c,
Well, yeah, because that's saying that, all this is saying is that whatever the function, whatever goes inside there is just the function that we're
so
differentiating.
if it's just one number, then it's 0.
Yep, or if it's pi, or if it's, any number, right, any
And
number.
you can't have x's.
No, can't have any variables in it, right, okay? So another way of writing this problem would be something like this. If we said y equals 7, then dy dx is what? 0. Okay, agreed?
Yes.
Okay? All right. Next issue. Okay, before we can get to the next issue, we need to review something real quickly. I want to review Pascal's triangle. Okay, Pascal was a real smart guy. He came up with lots of good stuff. We named a triangle after him. Here's how it works. So will you tell me, you remind me, how do we build Pascal's triangle? What's at the very top of Pascal's triangle?
And 1.
A number, and that number is 1. Good. Okay, here are the rules in building Pascal's triangle. As we work our way down the slope of the triangle, we're always going to go, the numbers are going to be offset. So we're going to go down to the left and down to the right to create the next two numbers. Okay, the outside numbers are always 1. So the second row is pretty boring. Okay, but now, when we get to the third row, things get a little more interesting. So this number is going to drop. We're going to have to fill in these 3 spots now. The numbers are offset, right? So we're going to have outside numbers of 1, and an inside number is always going to be the sum of the 2 numbers that are above it. So 2. Good. Okay, and if we keep going, let's fill these in. So what's the next row? What am I going to get?
1, 3, 3.
Next one?
6.
See how we're getting these?
Yeah.
We're just adding the 2 numbers that are above, add to form the number below. Okay, last row that we'll do.
5, 10, 10, 5.
5, 10, 10, 5. Good. And we could keep going with that. Pascal's triangle is really only useful if the if it's representing a binomial that's relatively small. So it falls within, the first so many rows. Okay, what's this thing for? Well, what this thing really does for us is each of these rows corresponds to a binomial expansion. So it's something, they're answering the question, what is the quantity a plus b to the n? Okay, they're helping us answer that. Okay, they're giving us the kind of the only part that's not extremely predictable of that expansion. So we're going to number each of these rows. The first one is n equals 0. The second one is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. If we get down at all far beyond that, Pascal's triangle is no longer very practical, and what we do instead is we just write out the binomial expansion formula, which is something that you could just Google. It just gives you, I'll write, well, no, I won't. I don't even want to write it out. It's not, it's used in statistics a lot. It just gives you a general expression of what this would look like for n instead of a specific number, right? Okay. So if we used a really big expansion, we would want to just use the binomial formula expansion for that and just plug and chug, right? But for relatively small numbers, this is a pretty easy way to do it, okay? So what does this mean then? So what this is telling us the coefficients of this expansion. So for example, if we took, let's just take n equals 3. Let's take that row. If I take n equals 3, so I'm expanding a plus b cubed. Roll up a little bit here. Then what this is telling me is the coefficients of that expansion. So I know when I expand this out, I'm going to get a 1, a 3, and a 3, and a 1 for my coefficients. What about the rest? Well, the rest is going to correspond to the powers of a and b, and it's very predictable and symmetric. I want you to notice some things here in math. It's really important to see and appreciate symmetry when you get it, because it makes life a lot easier. Notice that this is a symmetrical triangle, isn't it? Of course, right? So the numbers on the left are exactly mirrored by the numbers on the right, okay? Well, doesn't it make sense to you that if I expand something like a plus b to the n, that's got to be the same thing as b plus a to the n,
Yeah.
right? Doesn't that make sense? Because a and b, there's no preferential treatment there. They're both just either numbers or variables or something, right? So we've got to have a real symmetry when we write this out. Does that make sense? We should expect there to be symmetry. There's no reason that there shouldn't be. So we see it down here. What we do, the pattern is, we know that the product of the factors a and b has to always, the sum of the exponents has to always be n, which is 3 in this case. So we're going to start off with all of the weight shifted to a. So we're going to get 1 times a cubed times b to the 0. And what is b to the 0, by the way?
1.
It's just 1, so we wouldn't even write it, okay? Scoot over to the right. Well, the a's are going to ratchet down by 1 as the b's ratchet up by 1. We're going to get 3a squared b to the 1, right? Plus 3a to the 1 b squared plus 1 a to the 0 b cubed. Or as we'd write this instead, we just write this as a cubed plus 3a squared b plus 3ab squared plus b cubed. And there's our expansion for the quantity a plus b cubed. Right? Does that make sense? Okay. The nice thing about this is, well, let's try this once with actual like numbers and variables.
Numbers, yeah.
What if we do something like 2x minus 3 cubed? Okay, well, here's our expansion, right? We could quickly use the Pascal's triangle to come up with what the expansion is going to be. Now we have to just plug in our values of a and b. So what is the first term going to be?
2x.
Okay, I heard 2x cubed,
2x
and I
cubed.
heard 8x cubed, and they both could be right, but we have to be particular.
2x cubed.
2x cubed.
Meaning the quantity 2x cubed, right, which ends up being 8x cubed. So whatever, this is a, isn't it? The whole 2x is a. So this first one's got to look like the quantity 2x cubed plus 3 times,
2x
good, the quantity 2x
squared
squared
times
times, what's b?
Oh, 3. Negative.
Negative 3 plus 3 times 2x times
Negative 3.
negative 3 squared, good, plus negative 3 cubed. And if we were to simplify that, that's just going to give us, what do I get from that first term? 8, good, 8x cubed, plus, what about here? I'm going to get 3 times
12x.
4, it's 12 times negative 3.
Negative 36.
So we're going to get a negative,
Wait, where did you get that?
you see that? Because I've got, if I distribute the 2, this is going to give me a 4x squared, isn't it?
Times,
Times 3 times negative 3.
so negative 36.
So negative 36x squared, right?
It's,
Okay. Plus 3 times 2 times negative 3 squared. What's negative 3 quantity squared?
9.
Positive 9. So 9 times 6 is 54. X. And then negative 3 cubed.
wouldn't it be x squared?
No, just x.
Plus 9.
Because that one's to the 1.
Negative 9.
Okay, make sense? Okay, so that's Pascal's triangle. No big deal, right?
It's pretty good.
Very useful. Very useful. Okay, why do I bring this up? Well, it's come up a bunch anyway. I promised you I was going to quickly review this. But today it comes up for a really important reason. Today what we want to do is we want to come up with the big daddy of derivative shortcut formulas. You're going to get a lot of mileage out of this one, all right? This one we want to come up now with what is the derivative with respect to x of x to the n. Okay, this is a big one. We can come up with this one. This saves us a lot of time and energy having to do those doing the binomial expansion every time we have to do a derivative, right? We're going to do it once, very generally, and see if we can define a recognizable pattern in the result, right? We can discern one, I should say. So let's start off, let's start off, I jumped the gun a little bit. Let's go ahead and write down our general form that we have to match first. So what is f prime of x equal to again? Limit f of x plus delta x.
Minus f of x all over delta x. As the limit at delta x.
Good, okay, so let's make this specific to our function. So if f of x is x to the n, what is f of x plus delta x? Right, so we're going to have a limit. It is a good question. So we'll color code this. So what is this guy going to be? Does that make sense? If f of x is x to the n, what's f of a? A to the n. Yeah, what's f of b?
B to the n.
What's f of the quantity a plus b?
The quantity of A plus B to the n.
Good. So f of x plus delta x must just be the quantity. Good. Okay. Minus f of x is just
Minus x squared and x.
x to the n. Good. All over delta x. As delta x goes to 0. What would happen? Could we try to evaluate directly yet? Take the limit? No, we haven't done anything. Right? We haven't canceled anything. So obviously that's not going to work. We're just going to get 0 over 0. Now what though? We don't know what n is. So
Expand.
yeah, okay, we're going to expand. We're going to expand. Now this is a little bit hokey though, isn't it? Because n could be a billion, which would be I have to write a lot to write that one out, right? So we don't know what n is. It's indeterminate what it is. It's undefined. But we know that we're going to establish a pattern, and maybe we can see a pattern that's going to be good enough. So if I write out the first 3 or 4 terms, we can see something that we can guarantee is going to happen for all terms, right? This is probably the first time we've ever done a proof like this. This is kind of cool. So let's do that. So this is equal to then the limit as delta x approaches 0 of what? What is the red part going to become based on our binomial expansion? Now let's see if we can see what's going on here. If I go back one page, I want you to see if you can find a relationship between, like, what's going on between the n equals 5 or the n equals 4 and what the subsequent terms are. Outside one's always 1, isn't it? What about the first row? Can you see the kind of the first diagonal, I guess? Okay, in fact, doesn't that, it goes up by 1, and look over at what n is for each one. It looks like it's just n, isn't it?
Yeah.
Right? Okay, what if we keep going with this one just a little bit? I probably should have centered this just a little better. Yeah, what's going on? We gotta find a pattern there. And if we couldn't, we could always just use the binomial expansion. Just Google it and use that. But we're not going to. We're not going to cheat. We're going to see if we can come up with this. This is good practice. For n equals 6, you having to scrunch, but that's a 1, and then what do we get? A 6, and then 15, 20, 15, 6, and 1. Okay, so what about
Yeah,
this?
they keep going up by 6.
Little things like double and then,
Yeah, what's going on there?
That
Can
one
you,
goes up by 2, 3, 4, and 5.
Ah, okay, yeah, look what's going on there. They're going up, the amount that it's increasing by
Oh, that's
is,
weird.
is
And
what?
then on the next row, it's the 4 and the 10
36.
doubles each time it adds, right?
Oh,
Wait, now I can't, wait, what?
okay.
Because
Okay, I
it
got
goes,
lost
it goes
in
up by
the
3, then it goes up by 6, then it goes up, oh, no it doesn't.
Huh.
You're still, like, you're adding and,
But I'm not, but, kind
you're
of, but
adding
not.
one, you're adding what you did before, but then add one, so
So
like.
it's like if the one is
Three.
in the row and
No, because what about 6?
You're right.
you go.
Can we do 7?
Sure. Here, I tell you what, we gotta make this a little bigger. I'm gonna go ahead and redraw this triangle so we can see it a little better, because that's helpful. You can see more rows. But we're trying, and this is called inductive reasoning, by the way. This is a big thing in math. We don't practice this very much. Our culture, we tend to solve things deductively, where we're gonna try to say, if this is true, then this is true. We're highly logical people. But inductive reasoning is something that other cultures sometimes use better than we do. Inductive reasoning is where you're just gonna try to see, oh, there's a trend there. I see a pattern, I'm gonna latch onto that pattern, and it's both good and bad. Inductive reasoning is to make a long story short, inductive reasoning is partially responsible for our thirst to go just try to extract all the resources greedily from the rainforest, because the native peoples over long periods of time have inductively found that if I grind this leaf up and I put it under my armpit for a while, then my headache goes away. And so we send people out that record all these observations, and then we make drugs out of them, right? That medicine out of them. But these are things that we couldn't necessarily do in the lab very well. How do you know, where are you gonna start? And this is kind of an interesting discussion. Where would you start if you wanted to just come up with some kind of a medicine that's gonna help a headache? I mean, how would you know where to begin? It's very difficult. It's difficult to possibly, make some kind of educated guess about what compounds are gonna cause that effect in the human body. But people that have watched this, just have observed over long periods of time, can oftentimes make a really good connection between the things that they're doing and the effects that it's having on their body, right? And so that's why I say, we're not very good at induction, but I'm kind of digressing here just a little bit, but it is an important logical skill. So let's practice it a little bit. Yeah, we're doing it again. I'm going to make it bigger this time. Yeah. Yeah, you bet.
Hey, what happened? Whoa, now you're going. Do it up to 10.
I turned it around for 1 second.
Okay, I'll do one more.
Oh, man.
8. 28.
What do we got? These are getting kind of big now.
56.
Etc. That's probably all we need.
70.
No.
76.
Well, we're only looking at diagonals anyway.
At least do the 70.
Okay.
Okay, just give me the.
Because then you just go down.
56, 28, 8.
Okay, so can we see a connection there?
Yes, I know. The ends, you add the ends.
15, 6.
So 1, you add 2.
I get the second row. So I'm like,
Add 5, 15, add 6, 21.
Oh, and let me put the ends out here too, right? The ends were 0.
Yeah, that's what it adds.
Right, we got to connect them to these. That's the important part. So there's 0. Oh my gosh, I'm missing the one.
There's a relationship between the one.
You add it to the end that was before.
0,
So like 1,
1, 2's got to produce that. 3's got to predict that. 4's got to predict that. 5's got to predict that. 6, 7, 8.
So like, it's like,
I see how you get the first one.
it's like to the power.
You can take whatever you have.
I was like, right.
You know, like,
No, because then if you add 4, would that be?
You're onto something, sort of.
So if I took,
How am I gonna get,
Add 4.
this one's easy, right? This one is just equal to n. But what is that relationship?
The n before it, you add the n.
No?
You add the n.
and plus one.
Yeah, because it's like.
Okay,
goes to-
the n plus 1 is a part of the answer, I'll tell you that.
No, but like you add the 1 to the 2, and then you add the 3 to the 3, and then you add the 6 to the 4, and the 10 to the 5. That's what you do. You know what I'm saying?
Just keep building what you add on it.
Yeah.
oh, I thought you said.
I don't know how you
Ah,
guys
okay.
Like, that's the relative, you add that to it.
Okay, I'm gonna give you a big hint here. There's a really big hint.
We just got it, we got it.
Well, okay, kind of, you're almost there.
Got it.
You guys know the pattern, you need to get the formula.
I want a formula. Look at that triangle.
Oh, God.
Look at that triangle, etc. Can you connect the numbers in those triangle, in that triangle?
No.
You're trying to produce this one, right? So this is the result. Can those two numbers produce this number in the same way that those two numbers produce that number? In the same way that those two numbers produce that number?
No.
Yeah,
Yeah.
5 plus 4 is 9.
yeah, you're right.
You do? Oh, you do
Here, I got it, I
Then
just
minus
got it.
1.
2 times
Oh,
3 is 6 minus 6.
Ah, there it is.
Even if you add.
Jennifer, say that again. Say that again.
Okay.
2 times 3 is 6.
Half of 6 is
Half of 6 is 3. 3 times 4 is
12.
half of 12 is? 4 times 5 is
20.
half of, you see it? 6 times 5 is 30. Half of 30 is 15.
Golly, I think he's got it.
Okay, so now, okay, hold on. So now let's connect. How are these two numbers connected? Let's take this first triangle. How are those two numbers connected to n, which is 3?
It's the same.
It's 3 times, it's n times n minus 1, right? See, look, the top number in the triangle is always one bigger than the bottom left one, right? You see the pattern? Okay, so what we're really getting here then is this formula right here.
Not plus one,
Yes, I was right.
maybe minus one.
Oh, minus 1, sorry. Whoops. You're right. Okay, good. Anybody want to speculate what the next one is?
No, that's
There is the next one.
I'll give you just a couple seconds to think about
Like
this.
row 9.
So like if we did,
Oh my land, oh my god.
Oh my god. Two.
Let us think about it.
I'll let you think about it for a second.
No, just kidding.
10, 6.
It's just one number bigger than the other answer.
It's just
Oh, I found it.
This is a pretty-
Divided by 6.
This is a pretty tricky one.
No?
If anyone gets it, I'll pay them.
So what do you think it is? So 4 times 3 times 2 is what?
Divided by 24.
24 divided by what is 4? Yeah.
6.
Try it again. See if it works again.
Wait, I'm confused. Say it again.
See if it works again.
Okay.
6 times 5 is 30.
Times 4.
Times 4 is
120.
120 divided by 6. 20.
Wait, why is
Where
it
did
not
I get 6?
Well, just because that's the way it seems to work. Let's try another one.
Number 6. Well, I don't think I
There's
can.
6
That's an evil.
Okay, this is bigger.
Well, then why-
Okay, this is a bigger one. Hang on. We can make this easy though. Look at this one. So would you agree that 8 times 7 times 6 is a big number?
Yeah.
But whatever that number is divided by 6 is just 8 times 7, right?
Yeah.
56.
So what does the 20?
Oh, that was so-
28 have to do with it?
Oh, no.
So like 60.
See what I'm saying?
Now.
So here's our third one. Our third one is,
It's because there's 6 numbers and then there's 4.
oops. So you tell me, hey, I know this is really is cool and you're excited, you just want to talk about this, it's so darn cool. But tell me, what's the formula? N times n minus 1 times divided by,
6.
yeah, that predicts those.
Yeah.
Yeah.
Divided by 6 is there 6 numbers in a triangle?
Oh,
Yeah, I gotta make a big triangle now. Yeah.
no, you don't, but it's a good observation. Yeah,
What?
it's a great observation. that there are 6 numbers in the triangle, and so is that why you divide by 6? It's not, but it's an interesting observation. So we could keep going, and what do you think would be if we kept going? And it's getting kind of just for fun. Let's just see if we can make a speculation. But then we're just really overkill. But what about the purple triangle? What if I went clear out in the purple triangle? What do you think? 5 times 4 is 20.
Yeah.
Times 6 is 120. 120 divided by what is 5?
12.
120 divided by what is 5? 24. Okay. So is 24 the magic number? Let's try it. Let's try it. I need a little better, we'll use light
Why
blue.
24? Why are you turning up to 6?
24 times
Okay, so let's try this. Let's try this now. 24 is just 6 times 4, isn't it?
Yeah.
Right? So if I take the product of 7 times 6 times 5 times 4 and divide it by 24, it's just like dividing away the 4 and the 6. What am I left with?
35.
What do you know? How about that? Right? You guys could go live in the rainforest now. It's great.
Hey, we got the rainforest.
I just copied what they said.
Okay, so this pattern right here then is what?
N times N minus 1 times N minus 2 N minus 3 divided by 24.
Okay, good. Can you maybe even tell me now if we wanted to be even more specific? This is furthest
Oh
I've
yeah,
ever,
you can.
furthest I've ever gone with this with a group. This is pretty good.
Oh, this is awesome.
So I want you to tell me then, how could these numbers on the bottom are a little bit hokey. Can we come up with maybe a better way of guessing what those numbers are going to be? This worked pretty well, didn't it? I mean, we could actually use Pascal's triangle to keep predicting them. But how am I getting n equals 2? Well, okay, how am I getting this? If n equals, this was for n equals 2, right? Well, hang on a second. No, never mind. It's just for n. What is the number on the bottom? I'm saying this very poorly. How do you predict? How do you go from 1 to 2 to 6 to 24?
Ask Jenny.
So it's 2 times 3 is 6, and 6 times 4 is 24.
There you go.
Then 24 times 24 is 25.
Wait, I wasn't listening.
Okay. Okay, Jenny, notice something here.
And then you just add
1 times 2 is 2. 2 times 3 is 6. 6 times 4 is 24. So the next one would be 5 times 24, which is 120. Yeah. Make sense? Okay, so then if we wanted to write this formula out, we could actually start to write out the binomial theorem then. What we've really got here is, we've got, if I want to do a plus b to the n, what I've really got here is 1 times a to the n, right? Plus, my next number is going to be given to me by that, right? N plus n times a to the n minus 1 times, what's the power of b going to be?
0.
Got to be 1, because they got to add up to n, right?
Times B.
Okay, times, that's times.
Okay.
It's a times sign. Plus, my next coefficient was n times n minus 1 over 2, right? Times a to the n minus 2, b to the 2,
That one's a times two.
times.
I don't get it.
Okay, well, because now look what we're doing. With a binomial expansion, hang on a second, aren't these just giving me, these are just giving me the coefficients, right?
Yes.
That's what these formulas are giving me. For a certain value of n, they're just giving me the coefficients. Like if n equals 3, we're getting 1, 3, 3 times 2 divided by 2 is 3, and then 3 times 2 times 1 divided by 6 is 1. Right?
Yeah, but how does that have anything to do with the
So do you have to
Okay, you'll see. You'll see. Oh, we're getting there.
formula?
Right?
You had me, but then
So is that
I'll get you back.
Okay.
Plus n times n minus 1 times n minus 2 over 6, a to the n minus 3 b cubed, etc., right?
Oh my goodness.
What's n minus 3?
Oh, okay, I get you, I get you.
Doesn't it just keep going on?
It does, it goes on forever.
So the
Okay,
next one
but
would be n minus 1, n minus 2, n minus 3 over 24, and then a to
Exactly.
n minus 4b.
the last step here, though, is these darn numbers. We don't want to write the numbers down. What we can write instead is this. It's just, everything is going to be divided by, the first one is divided by 1 factorial. The second one is divided by 2 factorial. What's a factorial?
No, it means everything.
number,
I don't know, I remember I had it on my test.
So 4 factorial is just 1 times 2 times 3 times 4. Right?
oh,
Remember that?
oh my.
So 5 is 4 times
3 times 4 times 5. Yep. Okay. So then what is this one here? It's not a 6. It's really just a 3 factorial. Well, notice, look at that 3. That 3 shows up there and there.
What's the last?
How about that? You see the pattern?
No, Mr. Williams.
Oh,
What's the last, I don't get the last part, n minus 1, I still get the last bit.
so this is the number. So okay, so what's the next one? Shh. So the next one's going to be n times n minus 1 times n minus 2 over 4 factorial. Oh, you gotta be kidding me. We need like 3 consecutive periods.
I know, you see like, oh, let's go for the